Hi students, welcome back to geology. Now that we know about plate tectonics, continental drift, how the ocean floor is splitting apart at these divergent plate boundaries, let's talk about what happens when a plate just bumps into another one. Okay, so this is going to be transformed plate boundaries. Your pondering question here, why would sliding plates create earthquakes but not volcanoes? Okay, so we learned in divergent plate boundaries, things are opening up, allowing for mantle material to fill in. We'll learn at convergent plate boundaries how returning material will help create volcanoes. But when something is just running into another rock, when one rock is running into another rock, why would it create an earthquake, so ground shaking, but it wouldn't necessarily create any volcanism or volcanoes? Okay. So this slide's going to be on every single one of these just to bring you back. Remember, the lithosphere makes up the plate. That's the crust and uppermost solid of the mantle. Sorry. Yeah, uppermost solid part of the mantle. And then the asthenosphere is the upper mantle that is weak and it's ductile and it allows for the plates. Remember the cookie and the cream. The cookie is the lithosphere and the cream is the asthenosphere. Okay. So again, now we are looking at transform plate boundaries. We went over these in the last one. Divergent constructs things from tensional stress. Convergent destroys things from compressional stress. Now we're looking at transform plate boundaries where there's nothing being created or destroyed. We're just sliding right past with shear stress. Okay, so transform plate boundaries happen when two plates slide past each other. When we look at these boundaries, a lot of the time we're looking at them in map views. These are some cross sections. This is a cross section showing you that movement. But in general, we look at their movement and their behavior. We're looking at it in map view, so top down. Whereas the other two, because things are being pushed together or pulled apart, we're oftentimes looking at them in cross section. So there's no creation or destruction happening here. Crust isn't being created. New rocks aren't being formed. We're also not destroying them. It's just sliding past. So at best, we're going to have some offset of features. So things might not be aligned anymore. And we're going to get earthquakes. All right. So when things grind against each other, the ground's going to shake. So imagine bumping your shoulder into somebody else. There's a little bit of, shaking, right? That happens at transform plate boundaries, but there's no mechanism for creating volcanism. There's no magma upwelling. There's not these crevices being created. We're not returning rocks and changing the chemistry of the mantle. None of that is happening. So we're not going to see any volcanism. We're just going to see earthquakes and rocks essentially crumbling. So at transform plate boundaries, when we're looking at like the lithosphere, for example, you take that cookie, you break it apart, and you slide it past each other really fast where you broke it, you might see some crumbling in the middle. And so that's what the left-hand picture is showing you here. This is the transect of the San Andreas Fault in California, which is one of the largest transform boundaries on Earth that separates the Pacific Plate and the North American Plate. It's really interesting in California. This fault separates those two plates. And in some places it's locked, and some places it's actually moving pretty regularly, or we call that creep. So in the central coast of California, we see creeping. So slowly but surely it's moving along. And then in the north and in the south, it's locked, and that is dictated by the rocks. So the rocks in the north and the south are much stronger rocks. They have interconnecting crystals that interlock with each other, and it doesn't allow for any movement. It's really hard to move those rocks. In central California, central coastal California, we have something called serpentinite. And serpentinite is very slippery. It has asbestos in it, and it allows for easy slip. And so we get a lot of creeping or slow motion along the San Andreas Fault, in that region anyway. We're not unique, though. California is not the only place there's transform plate boundaries. There's New Zealand. This one is the North Anatolian Fault in Turkey. This fault runs east-west. Ours runs northwest-southeast. And this one runs more of an east-west transect. And it is the interaction between the Eurasian plate and the Anatolian block, which is part of the Arabian plate and the African plate. And because that Anatolian block or that Anatolian plate is moving to the west in relation to the Eurasian plate, it creates this transform boundary or this transform fault here. This fault is troublesome because there's a lot of issues with building construction. A lot of their buildings are not equipped for large earthquakes, and the North Anatolian Fault a couple of years ago produced a magnitude 6.7 to 7 on the Richter scale magnitude earthquake, and that devastated this area because they were not prepared for it. It isn't a fault we didn't know about, so we know that it's there, but in Turkey, they don't have the infrastructure that we have in California or even Japan to withstand earthquakes of that magnitude. So some final thoughts for transform plate boundaries. So that was transform only. Describe how a transform plate boundary can create earthquakes, but why there are no volcanoes. So why did I describe that there were not volcanoes at this boundary, but there will be earthquakes? I will see you guys in the convergent plate boundaries lecture. Bye.